Hi, everyone. I decided to do this talk in English. I really don't recall why, but I committed to it, so let's do this. So first of all, thank you for the intro. It was a bit more interesting than I thought. Everyone keeps asking me about intermittent fasting, but we won't do this now. So what is this talk about? We're going to talk about vector similarity search. Now, I've been in a conference about search 2 weeks ago in New York, in Virginia actually, and it's like all the rage now, and it's a bit more popular than I thought it would be. So it used to be some sort of a niche search engine, and now it's everywhere, so it's really worth paying attention. So the agenda for today, first we're going to talk about me, about ARG Max, what do we do, and why do we care about vector similarity searches. Then we're going to talk about what is recommendation system and search, and why I think they are essentially the same thing. Then we're going to talk about approximate nearest neighbors, and why do we need to approximate things if we can calculate it exactly. Then we'll talk about the huge safari of similarity search stores, and there are a lot. I'm not associated with any of them, so feel free to criticize them, and just kidding. And then I'm going to talk from our perspective as an application provider, how do we see the new standard forming of vector similarity search as a service. And then if we'll have time, we'll have a short Q&A. Please don't ask questions during the talk. It really interferes with the video. Okay, so let's start. This is me and my two sons. My wife is kind of missing from the picture, but she's the one taking it. I started my way in machine learning at Microsoft, working on the Kinect. Kinect was this 3D sensing device that was really cool and went away, essentially because of deep learning. So I know a lot of computer vision, but old computer vision, I think before deep learning. And then I got into the field of natural language processing with my work at AT&T. We worked a lot on customer service data, proactive care. It was a really interesting job. Then I went to work for Yahoo. And I got I don't know, I wouldn't trust myself with the permissions that they gave me. I got the permissions to read like any Yahoo inbox mail ever, which is interesting. But I assume that these days they don't do these silly mistakes. Just kidding. And then I went to found best practice. Best practice was an NLP plugin for lawyers in the legal tech domain. We were operating for 3 years, and then we got acquired by Litera Systems in New York. This was kind of my segue into legal tech and into recommendation systems, having the need to recommend suggestions. It was a very interesting experience. And ever since then, I lead Argmax ML, a consulting firm on recommendation systems and natural language processing. Aside from working, I also host the ExplAInable podcast with Tamir Nave, and I co-organize the PyData community with Dean and Ido that are somewhere in the crowd. That's it about me. Let's say a few words about Argmax and why do we really care about search. So we do mostly recommendation services, recommendation system services, but when trying to look into our customers and cluster them together, we see 3 main clusters. It could be either gigs from the creator economy, and I work with some of you. Hi to the Lightfix guys in the crowd. And we worked also in retail, in the financial domain. But most of our work is actually centered on advertising, where we have a lot of really big data and scale is an issue. And essentially, you're trying to find lookalikes. But from our perspective, it doesn't really matter the domain. The underlying architecture is mostly the same. In most cases, we take features, we transform it into vectors, and then we try to find lookalikes or nearest neighbors. So it's really, vector similarity searches is our working horse. We use it all of the time. So let's talk a bit about recommendation system. Now, from my perspective, and this is a bit of an, not everyone agree with me about this definition. Recommendation systems and personalized search are the same things. They might have different traditions and different literature, but from my perspective, as someone who's writing the applications, those are two sides of the same coin. So what is a recommendation system? Essentially, when you develop a recommendation system, you have a lot of items. These could be advertisements, this could be products, and you know something about the user, her history or user features, and you have limited space, right? So the limitation of space, this is what caused the problem to be formulated as a recommendation system. And you need to make an informed decision what ads or creatives or products to show and in what order in order to maximize something. It could be clicks, purchases, long-term engagement, or whatever. Now, assuming that there's like, in the recommendation system, you can think about this big imaginary matrix in which you have like the users in the rows and the products in the columns, and you're trying to predict the user preferences. This is like the classic formulation. Now, in practice, we don't usually model on a user level. We usually model on some sort of aggregation, user segment or user features, and we try to predict the percentage, right? What is the likelihood of a click, the likelihood of a purchase? So it looks something like this. We have this huge imaginary matrix that no one actually stores in memory, and we try to predict for John, which is from a specific segment, what is the likelihood of buying cookies. One way of doing that is to model both the items and the users as vectors. And I'm not going to talk too much about how do we do that? How do we transform user into a vector or an item to a vector? But essentially, what we're trying to optimize is that the multiplication or constant similarity or any other metric of the user vector. And note that we have this arrow above the icon, which means that it's a vector in this presentation. The multiplication is going to be approximately that conversion rate. Right, so if we train our model somehow, this is our goal. And note that this formulation is actually pretty expressive because we can use it also for user-to-item recommendation and also for item-to-item recommendation. In most recommendation system use cases, we have people like you liked whatever, these songs, folk metal or any other kind of esoteric genre. Or we have people who listen to that song also listen to other songs. So those two use cases are pretty linked. So without going into too much details about the implementation, there are roughly two approaches, either content filtering or collaborative filtering. Collaborative filtering relies mostly on user behavior without taking into account user features. And content filtering is, in theory, the other extreme of using only user features, for example, the product image, the product categories, the product text. In practice, most people do something in the middle, use some user features, some item features, and they get the best of both worlds. Cool. So from my perspective, search is essentially the same, right? I have a query. It could be a textual query. It could be an image. Don't really care. I encode it with some sort of fancy model into a vector. I do the same for the items. It might be the same encoder. There are also very interesting models like a CLIP that actually are trained to optimize images and text to the same embedding space. There's a lot of very interesting work. And to be frank, it's really hard to keep track. There's like, I don't know, you go to sleep and there are like 3 state-of-the-art models every night. So this presentation could be outdated by the time we finish it. And essentially, you're trying to optimize such that the score could be, in most cases, it's constant similarity or inner product. It should be roughly the conversion rate we are looking for. So this is search. In search, it's called relevance. In recommendation system, we have some other metric, but from a design point of view, it's the same thing, right? And if we want our search to be personalized, then cool. Now we just need to encode also the user features. Where's the user from? What is the user history? But same thing, right? There's not much difference in the architecture. So we have vectors. We have a lot of vectors. From the perspective of this presentation, we're not going to talk about encoding the vectors, but what do we do with them? Right? We have a lot of vectors. We can concatenate them. We need to search them. Cool. So that's not that trivial, especially if you're trying to build a data pipeline. So let's talk a bit about approximation algorithms. And before we talk about approximation algorithms, here is like, I don't know, a 4-liner minus the boilerplate of an accurate search, right? Thanks to sklearn, scikit-learn. This is pretty trivial, right? I'm going to import the default k-nearest neighbors, and now I have a vector search. That's it, right? So problem solved. Why do I really need all of these fancy vector similarity stores? And there are several companies that raise a lot of capital. Why do we need all of these, things if we have the problem solved here, right? So let's talk about scale. While in theory, this naive search, also called flat search, works, let's try and evaluate how many floating point operations we need to do when we have a lot of data. So essentially, we have M users or M queries we're trying to query. We have a lot of items, right? We wouldn't have a recommendation system or a search if you had only a few items. And all of these vectors have a certain dimensionality. We need to do all of these multiplications, which is a lot of time. You can think about the scale. And then we need to rank them, which sorting is also not trivial, and we need to do it a lot of times. So when you have a lot of vectors, it becomes a bottleneck for the entire system. And on the other hand, flat search is the most accurate things you can do, right? It actually calculates the metric. You don't make any sacrifices regarding accuracy, but you are very limited in the number of items that you can actually store. So let's talk about approximation algorithms, and there are plenty. I'm going to talk about the 3 major families. And there are others. For example, you can just try and quantize the vectors, right? Maybe I don't need a floating point precision of 64 bits. Maybe I can use 4 bits, right? So there are a lot of neat tips and tricks. But let's talk about algorithms and how they're implemented in vector stores. So the first way, and the most dominant way, is the hierarchical search. This is the mechanism behind HNSW, and HNSW has been incorporated in all major vector stores, including classical databases like Redis and Postgres, if I recall correctly. And the idea goes as such. Let's assume that I'm looking for John, which is from Seattle. And I'm asked to find John's k-nearest neighbors. So there's no need to search and compare John to the entire world, right? I can look only in the United States, or more specifically within Washington State, or more specifically within Seattle, or even more specifically within John's zip code, right? So I'm saving a lot of comparisons that I do not have to do. On the other hand, this hierarchical representation, even though it's pretty useful, it does introduce some sort of error. For example, what if John lives on the border of Washington and Oregon, right? His k-nearest neighbors might be outside of the state, and I would never find them if I go with the hierarchical approach, right? So there's plus and minuses, and I think that this is the most common approach today. This is the heart of the HNSW algorithm, but it's not the only one. Another approach, which is more classical or more useful, especially when the vectors are sparse. A brief word about sparse vectors versus dense vectors. let's assume that I encode a document only by the word that it contains. So we can think about this reverse matrix in which I have in the rows the documents, and in the columns I have all of the possible words in the English language. So looking up all of the documents that have the hello world phrase, it's pretty simple. First, I filter out all the documents that have the word hello. Then I filter out all of the documents that have the word world. And all I need to do is to calculate the intersection, which is pretty efficient with hashing tricks and other algorithmic tricks. So this is the main idea behind reverse index. I try to index the vector entries and not the values to have pretty fast and approximate lookup. It works best for sparse vectors, even though it's also useful for dense vectors, also a very common technique. Right here, in the general case, you can think about ranges of vectors. Right, is the first entry of the vector between 0.5 and 0.7? There are a lot of very neat techniques. And the last one, which is by far the fastest search, but also the least accurate, is using hashing. Now, hashing is used in key value stores all the time. I think that every one of you used hash like this morning before the coffee. But we need a specific type of hashing function. We need our hashing function to preserve the distances in most cases. This is what is called the LSH, locality sensitive hashing. For example, a very simplistic hashing function is to only take the sign. Right? So here I have one negative and two positives. I can assume that this entry is more closely related to this than to this, right? Because they have that those two entries are further away than the middle one because they share some of the sign. Maybe it's an approximation, it's a very fast approximation, but when we have a limited amount of memory, this is usually the go-to algorithm. Okay, so a very short comparison. There are also other algorithms, but these are the main one, between the flat, which is obviously the most accurate, but also the most expensive. We need to store all of the vectors in memory. And on the other extreme, we have the LSH, the hashing, which is the most efficient both in runtime and in memory, but the least accurate. And in the middle, we have the HNSW and the IVF, which are a bit head-to-head. It really depends on the use case. I had projects in which the IVF was the better one, and I had projects in which HNSW was actually better. Generally speaking, the HNSW consumes more memory. So if you're trying to save a bit of cost on the machines, maybe HNSW could be problematic. Okay, so a few words about similarity search. So now we know how the internals of a vector search work. Let's talk about how to use it. This is the classic search framework, right? I have a user or a query, I encode it, and I need to find the most similar items. This is like the classic use case, and this is what people usually have in mind. But typically, we have some constraints on what we can recommend or suggest to the user. So for example, let's assume that this user, John, loves bagels and he eats them every day, and recommending a bagel for him, the user vector for John is like exactly the bagel vector, the same thing. But John traveled to Germany or some place in which bagels are not available. Even though this is a perfect match, there's no reason to recommend an item that is not available there. So here we have some sort of a pre-filter that we can apply depending on the context. Now, not all filters can be implemented as pre-filters, and as we can see behind the scenes, pre-filters are essentially duplicating the databases or only indexing the relevant items in the relevant partitions. Some filters, for example, is that item available in stock, are only known in real-time query, right? So we have our pre-filter and we have our post-filter. Like, cool, bagel is probably the best match, but we don't have bagels in stock currently. So usually after querying from the vector search, we need to apply some additional logic. It is either called post-filtering or re-ranking. Cool. There are a lot of vector similarity stores. Some of them try to take care of the pre-filtering and post-filtering for you. It really depends on use case. We use a lot of them. This moment, there's no like, I think that for small projects, my go-to similarity search is usually the FAIS, the Facebook AI Similarity Search. And what I like most about FAIS is that you can actually change the algorithm. It has like an index factor attribute that you can change even after you deploy the system and make it use HNSW instead of IVF, or even after the system is deployed, which is pretty cool. You don't need to change the code. But there are plenty of other use cases. We also implemented Redis when you needed the real-time feedback. And I take no sides. I have no commissions for recommending any of them. There are a lot of good solutions, and there are a lot of considerations that you need to take before choosing a provider. And if you're interested about speed, there's this website called the ANN Benchmarks, which compares all of the open source similarity search. And it's pretty cool. You can see like the recall versus the amount of requests. Pretty informative, and it gets updates. It changes like, I don't know, every week. So worth checking out. Let's talk a bit about considerations when choosing a vector similarity search. First of all, are the vectors sparse or dense? If the vectors are huge and sparse, usually we want to choose one of the most classic ones like Elasticsearch, Solar, Lucene, which are optimized for sparse vectors. If they are short and dense, usually an output of a model, then probably don't choose Elasticsearch, Lucene, or Solar. Use another one. Do we need to filter a lot of items? Do we want the filtering to be a part of the query process or not? Or are the filters predefined and not changing a lot? Are items being changed rapidly? Some of the algorithms can support changing items after they're indexed, and some do not. If we think about it for a second, let's take an algorithm like HNSW that try to build zip codes, neighborhoods, cities, etc. If you change too much items, then it won't work correctly, right? Maybe it's not located, it's not optimized anymore. So some algorithms support changing data before indexing, and some algorithms need to re-index the entire data set. And I think that the last major question is, do I query on real time, like one by one, or is most of my usage on a batch? So these are like the main considerations. And a few words from my perspective. We develop an application, right? We go from client to client, and we develop either a personalized search or recommendation. And from our perspective, choosing a vector similarity search is the same as choosing a database, right? I don't really care between Postgres and Oracle. I know that I use SQL, and it will work, right? I don't know if they use AVL trees or some neat hashing tricks. It's not really my concern. So what we try to do, since we work with a lot of clients and some of them have different agreements and different considerations, we try to write a wrapper in which we actually support the same API. I want to have a vector, I want to choose the metric, and I want to choose a K. For example, bring me the 5 nearest neighbor on the L2 metric for my vector. And I don't really care what is the provider behind the scene. So our library tries to abstract away all of the specific vendor-specific details. It is not as robust as what LangChain did, but I think that this is the approach. At the end of the day, the API is pretty simple. Here's my vector. Please bring me the k nearest neighbors, I don't really care about the underlying algorithm in most cases. So LangChain also have a pretty long list. I think that most of the similarity searches that I'm aware of are being supported or incorporated into LangChain. And as you probably heard like 10 times this week, you should probably get familiar with LangChain. It's like everywhere. So essentially that's it, just to sum up. So you have like the key takeaway from this talk. We think that vector similarity is the new standard. You're going to see it everywhere with existing database provider like Postgres, Mongo, Redis, all of them already have vector similarity incorporated in. And we also have a lot of vendor-specific, like Pinecone, that do specifically vector similarity. We have a trade-off between the accuracy or recall and the performance. And we can control them by choosing the algorithm. And choosing between an algorithm or a vector similarity provider really depends on the data that you're using. Are the vector sparse, dense? Do you use batch queries or one-offs? That's it. And I think we have like 3 minutes for questions. So thank you.